Welcome back to CS 712. In this session I'm going to talk about finite automaton, also known as finite state machines. This is the machinery that's capable of solving the recognition problem for regular languages. And again, I'm assuming this is review. Excuse me. So let's look at a simple example up here. Again, the notation I'm using is that this state with a, I don't know, less than sign sort of leading into it indicates that this is the initial state. A state with the double circle is a final state. And how does this thing recognize a language? And remember, a language is a set of strings, so we're really recognizing strings that are in the language. Well, we talk about the finite state machine accepting a string. And how does it do that? Well, it starts the initial state and it consumes the string one symbol at a time. It does that by traversing an arc that matches the current symbol in the string and then moving, sort of we have this pointer to where we are in the string, and when we traverse an arc we match the current symbol in the string and we move to the next symbol. So we start an initial state and we consume the string by following these arcs, matching symbols in the string. And when you're at the end of the string, if you end up in a final state, this one happens to be both initial and final state, then you say, I accept, the finite state machine accepts the string. Okay, so if I was going to match A, B, B, A, I would start an initial state, follow the A here, the B back, the B here, and the A back. The string is now consumed, and I'm in a final state, so that's the notion of accept. We accept that string. It's in the language recognized by this finite state machine. Again, down here, that's the terminology we talk about. The language of a finite automaton is the set of strings it accepts. Okay. Well, we can also feed it strings that aren't in the language it accepts. And what happens then is with the same idea, we consume the string by following arcs. And when we get to the end of the string, if we don't end up in a final state, then we say we reject the string. So if I try to match, A, B, B, I go A, B, come back here to B. I'm done. I've consumed the whole string, but I'm not in a final state, so I reject the string. Okay, and again, the language of a finite automaton is the set of strings it accepts. Okay, so a finite state machine can recognize languages. Well, it's useful to think about a couple flavors of finite state machines. One is called deterministic finite automaton, or DFAs. In this case, each state has exactly one arc leaving it for each alphabet symbol. Notice that as a shorthand, I don't usually draw the error arcs. So for instance, if we go back to the state machine that I drew on the prior slide, it was these three states. But what I left off was if I'm in this state and I see an A, it's really an error. And so what's actually happening, even though I didn't draw it, was that I would have an arc on A going down here to a sinkhole where I can never get out. Once I'm there, I just match A's and B's and stay there, and it's non-final, so once I get down there, I can never, if I follow that arc, I can never accept a string that contains that symbol. Okay. Well, going back to the notion of determinism, in a deterministic finite state machine, I always know what to do. Right? I always have just one choice. I'm in this state, I have to go there on an A or I go there on a B. Okay. So that's sort of easy to understand. I mean, I think you could directly program up. If you were given a deterministic machine, you could write a program that would do the corresponding recognitions problem solution. But it turns out it's useful to think about the non-deterministic version of this machinery. So we talk about non-deterministic finite automaton, or NFAs. And in this case, we might have more than one choice for a given symbol. So a state may have more than one arc labeled with the same symbol leaving it. Okay. Or The other possibility is we're allowed to label arcs with lambdas, which means we can take lambda arcs without consuming any input. Okay, so here's an example of using lambda arcs here. Again, I do A, B, and then I use a lambda arc to get back. So again, I think I'm recognizing the same language as the earlier finite state machines, but I'm using lambda arcs this time. Okay. So if we can get to a place where we have more than one choice, what does it mean to accept a string? Well, an NFA accepts the string W if there's a path from the initial state to some final state such that W is the concatenation of the symbols on the arcs of the path. Otherwise, the NFA rejects the string. So if there's some pathway, because there's potentially going to be more than one now with non-determinism, if there is a pathway that leads you to consume the whole string and finish in a final state, then you say you accept. If there is no pathway, then you reject. So sometimes people think about non-determinism as a sort of an ability to fork a copy of the recognizer at every point in time when you have a choice. And you send a copy of the recognizer down each arc for each choice you have. And you don't care if a recognizer fails. All you care about is if a recognizer succeeds. And if the recognizer that was created does find its way all the way through the string and ends up in a final state, then you declare success. And you only fail if all the copies that were created along the way all fail. Okay. A couple of technical points now that we'll use later is that all NFAs with more than one final state can be transformed to equivalent NFAs with a single final state. So the ability to have more than one final state is not really technically necessary. We can tighten it up. So here's again a finite state machine for AB star or BA star. And here's what I claim is a finite state machine that will recognize the language denoted by that regular set. Okay. And it has two final states, but I can get rid of those final states by just making the final states not be final in the new equivalent finite state machine and then adding lambda arcs to come to a special final state. Okay. So giving the user the ability to write more than one final state is really just a convenience. We can always squeeze it out and represent an equivalent machine that has just one final state. What else? Well, all NFAs with no final states can be transformed to equivalent NFAs with a single final state. And again, this is sort of the degenerate case. If I don't have a final state, I can't match any strings, right? So the only language I'm going to recognize is the empty set. Okay? But again, just to go through it a little bit, if I have this machine, for instance, this finite state machine drawn over this alphabet, it's just looping over A's and B's, and it never ends up in a final state. So it consumes all strings, never finishes in a final state. Technically, I can give it a final state by just adding the final state there, not connecting it to any arcs. And again, that language defined by that machine has to be the empty set because there's no way to match any strings. You can't get to the final state. Okay, one more little technical detail. What about the case where I have an initial state that is also a final state? Well, I can also break those apart. All NFAs with an initial state that is also a final state can be transformed to equivalent NFAs with initial states that are not final states. So I have this sort of scenario that we saw in the earlier examples. I can just break that into two states and connect them by a lambda arc. So this introduction to non-determinism will be useful to us to sort of simplify the key proof here, which is in fact that these finite state machines are the machinery required to recognize regular languages. So let's stop here.